All right, let's work on section 2.1, which is areas between curves. So this first theorem is if you have two functions, let's say f of x and g of x are continuous functions such that f of x is bigger than or equal to g of x for all x in some interval. So the picture that I have here is the visual behind that. So I have f of x, which is this green function, and then g of x, which is this blue function, where sometimes one of them is bigger than the other, but the important part that we're noticing here is in between the interval a and b, f of x is bigger than g of x. Then the area of the region bounded by those two functions between the lines x equals a and x equals b is the integral of f of x minus g of x. You'll often see it with parentheses there. You'll also hear a lot of people, including me, say quite simply, it's just the top minus the bottom. All right, and there's a nice visual behind that. If you think of this as Riemann sums, very similar to how you did in Calc 1, you can think of each of these little slivers. That's probably not a great box there, but remember, if I were to do Riemann sums, these are the rectangles that we're finding here. And if I zoom in a little bit, you'll notice one of those rectangles right here. If I were to do the entire rectangle underneath f of x, it would include this little extra piece that was underneath g of x, which is why you do one of them minus the other to find the area of just what's in between the two. All right, so that's the theorem that we have. So let's work through some examples. This first example, if R is the region bounded by the graphs of y equals x plus 4 and, sorry about that, y equals 3 minus 1/2 x, on the interval from 1 to 4, find the area of that region. So step one is to always draw the graph. Now I've got the graph already drawn here for you, but make sure you know how to come up with that graph on your own, either because you know how to graph a linear function, for example, or perhaps you use your graphing calculator, but make sure you know how to come up with that graph on your own. So y equals x plus 4 is a straight line with a y-intercept of 4 and a slope of 1. Y equals 1 minus, oh, that was a typo there. Sorry, that should have been a 3 minus, and it really is graphed correctly. A 3 minus 1/2 x is a linear function, so a straight line with a y-intercept of 3 and a slope of 1/2. And then I'm graphing this only between the x values of 1 and 4. So only between those two values, 1 and 4. This is my shaded in region. This is what we're trying to find the area of. You don't have to do Riemann sums, though you certainly could if you wanted to, but I always like to draw one little sliver to help me visualize what it is that I'm actually doing. There are technically infinitely many of those. If you remember Riemann sums, so maybe just one is sufficient for me to visualize which one is on top and which one is on bottom. And it looks like each one of those, again, infinitely many slivers, if I were to zoom in real close, they all have a little width right there of in the x direction. So that's why this is a dx sliver instead of a dy. So then I would say that my area is going to be the integral, and we're going to skip Riemann sums. We really are going to do the fundamental theorem of calculus, but it's worth your time to notice that this comes from Riemann sums. So the integral, the bounds are from 1 to 4, and it was the top minus the bottom, although there should be some glaring error to you right there. If you look, you do need these parentheses because it's top minus bottom. That negative really will have to distribute. Okay, so now it's correct. And then we'll simplify it. That becomes the integral from 1 to 4 of x plus 4 minus 3 plus 1/2 x. Don't forget that dx notation. And you'll often see that with the parentheses around the integrand. That's technically always there. I tend to skip writing that, but you certainly can keep those there to be more accurate. And then I'll combine my like terms. Looks like I have 3/2 x plus 1 dx. Then I do the antiderivative. So add 1 to the power, divide by the new power. The antiderivative of 1 is x. Evaluate that from 1 to 4. Of course, I've run out of space. So I'm going to go over here to this side. I'm going to give myself, oh, sorry, a little bit more space because I am going to solve this whole one completely. So then that becomes at 3 over 4 times 4 squared plus 4. And then minus, if I plugged in 1, I got 3 over 4 times 1 squared plus 1, and then type that into your calculator. Make sure you use that math fraction button in your calculator so that you can combine that to be a simplified fraction. Oh, and I typed that in wrong. I'm sorry. I did get 57. There we go, over 4. Ta-da! That's kind of the big picture of 2.1. Find the area between two curves. Step 1, draw the picture. Step 2 is going to be to draw that sliver. And I know you probably can get away without drawing it, but I don't recommend it, especially when you move on to 2.2. That sliver is going to be really vital because that sliver is going to help you visualize which one is on top and which one is on bottom. Okay, so I highly recommend it. You might get away without drawing it, but I do not recommend you skip that part. And then you do the area. It's going to be the integral of top minus bottom. All right, let's do another example. Let's see if we can visualize it this time on our own. So find the area of the region bounded by y equals x squared and y equals 4. So we're going to make a quick sketch by hand. Here is my pretend I'm a good artist. Y equals x squared, and y equals a number we know is a horizontal line. So y equals 4 looks like that. And shade in the region so you know what it is that you're finding. It looks like this is the region that I'm looking for the area under between those two curves. So I am going to draw my little sliver again. There's technically, I like to draw one of them. And then technically, remember, there are infinitely many. It's always worth your time to notice. It looks like all infinitely many of those slivers have y equals 4 on top, and then the y equals x squared on bottom. So this is really good. So then I have area is equal to the integral of top minus bottom. The only thing here that I'm missing so far are my bounds. So how do I find the bounds? You are going to want to find the intersection points along the way. Maybe you know off the top of your head, it's totally fine if you do. Maybe you use your calculator as a tool, also totally fine. I think this one we can show the work for even. I set the two equal to each other to figure that out, and I take the square root of both sides, and I got x equals 2 and -2. So my bounds would be from -2 to 2. And then another thing that you might notice from Calc 1 is that symmetry, that the area from 0 to 2 is exactly the same as the area from -2 to 0 in this case because both of those functions were even. So I can rewrite that as twice the integral from 0 to 2 of 4 minus x squared dx. It just makes plugging in numbers a little bit easier. So 2 times, now I'll do the antiderivative. And then make sure you plug in your bounds. Keep track of your equal signs, right? Your equal signs one on top of the other. You're going to have to be turning in a lot of work. So make sure you're clear to yourself, to whoever's grading it, that you know what it is that you're talking about. So show every step. So 2 times, if I plugged in 2, 4 times 2 is 8. 2 cubed is 8. And then minus 2 times 4 times 0 minus 0 cubed. So not too bad. And I ended up with 32 thirds. Again, let's leave that as an exact answer, not a decimal approximation. Ta-da. And we could write down units squared if we'd like to help us realize that we found an area. If that were a volume, that would be units cubed and so on. All right, let's do another example. Okay, well, I think it's worth our time to always visualize it first. Know that you're going to want to be able to graph them on your own. Feel free to use your graphing calculator to help. While you're working on these at home, practice with your actual TI-84 graphing calculator, since that's what you'll have with you on an assessment. So maybe check with Desmos to help you visualize it, but make sure you also know how to use your graphing calculator since you won't have Desmos during an assessment. So I'm going to graph this one. Find the area of the region bounded by y equals x. That's a pretty easy one. I bet we can do that without our graphing calculator, but there's my y equals x. And I also have y equals 7x, which is a straight line that's just a bit steeper. So here's my y equals 7x, and it looks like I have another one, y equals 21. Remember, y equals a number is a horizontal line. And I'm going to shade in the region that's bounded by all 3 of those. Whoops, sorry about that. Bounded by all 3. I want you to notice that this is the shaded region, that triangle bounded by all 3. This little triangle there on the left is not the shaded region, because the question never said I was bounded by the y-axis. So you have to imagine that y-axis isn't actually there. Okay, and then I'm going to draw my slivers. So I've drawn the picture. Now I'm going to draw my slivers. I'll zoom in a little bit more so we can visualize this better. If I draw my slivers, remember, I like to draw one sliver. So long as you remember, there are, in fact, infinitely many slivers. Because here's a problem. Notice that over here on the left, those slivers have the y equals 7x on top and the y equals x on bottom. But then suddenly they have the y equals 21 on top and the y equals x on bottom. That's two different top minus bottoms. So let's think about that for a second. It's going to be a little bit trickier, but we can do it. I'm going to find these intersection points right there. This one intersects at 3 and at 21. Being able to label that is really helpful. So I'm going to write this area really quick. First, find the integral from 0 to 3. That was that first half on the left where the 7x was on top and the x was on bottom. And then I could add in the 3 to 21 where the 21 was on top and the x was on bottom. I'll maybe draw those parentheses just so you can keep track of that along the way. This was finding the area of everything on the left first, and then the area of everything there on the right second, and then combining them together. And that would totally work. Right? That is a valid way to get an answer. You will go through, integrate, plug in some numbers, and it will work. I do want to show you another way because there was a way I could have made that slightly easier. So that's what I'm going to do next is I'm going to show you just another way. I'm going to look back at my picture. I'm still going to have this shaded region. And instead of drawing my regular slivers or my dx slivers, why don't I tilt everything on its side and do Riemann sums on its side and do a sideways sliver? Let me show you what that sliver is. Technically, remember, this is Riemann sums. So if I were to zoom in and find the area of that small little rectangle, Riemann sums we're using a rectangle, then I would notice that the width of that rectangle is actually on the y-axis. So the width is a dy, and then the height is in the x direction, so the height would be an x component. So it's worth our time to notice that that sort of sideways sliver is actually going to have a delta y if we were to do Riemann sums, which is going to be a dy in my fundamental theorem of calculus or in my integration. All right, so now we have that. I'm going to keep that picture here and I'm going to find the area. It's going to be the integral. We said dy, so I'm going to use a dy, and I still need to do like a top minus bottom, but instead of top and bottom, it's now going to be a right minus left because this is now a rectangle on its side. So it has to be that y equals x on the right, and then that y equals 7x on the left. So we just have to rewrite those to be the x equals y and the x equals 1/7 y. And so that's what's going to go in my integral, the x equals and the x equals on each side. And then my bounds now, because it was a dy, would be y values. And if you looked at your picture, it looked like it went from 0 to 21. The y-axis went from 0 to 21 of the shaded region. See, now it's only one integral. It's easier to integrate. So I'm actually going to do the calculations for that one. That would become the integral from 0 to 21 of 6/7 y dy. I just combined my like terms, and then I would get 6/7 y squared over 2 evaluated from 0 to 21. And if I plugged in 21 and then plugged in 0, I would end up with 6/14 times 21 squared, which if you're willing to trust me, I just typed that into my calculator and I got 189. Ta-da. If I were to go back and do the work for my first setup, all that work, I would have gotten the same number combining both of those integrals. Take a second, pause the video, see if you can do both of those integrals and still get the same number. All right, let's keep going with our area between curves. Another example is going to be sum with trig. So here's another example. I've got find the area of the region bounded by y equals sine of x and y equals cosine of x over the interval from 0 to pi. So I've got these graphs here for you, and then we're going to try to find the shaded region. Here I haven't shaded in the region yet. I want to point out that it's asking me to go from 0 to pi. So here is my x equals 0, and here is my x equals pi. You should notice now that between those two vertical lines, x equals 0 and x equals pi, there are in fact two shaded regions. And those two different shaded regions would be this first one over here on the left, and then this second one over here on the right. Those are two different regions that are bounded by both sine and cosine. And if I were to draw my slivers, just like we've been doing so far, if I were to draw that sliver, you can see that there's technically infinitely many slivers. Remember that. All of the slivers on the left region have the cosine function on top and then the sine function on bottom. And then all of those slivers for the right region have the sine function on top and then the cosine function on bottom. So we are going to have to break this up into two different integrals. The first integral is where cosine was on top and then sine was on bottom, and then plus, then the second one is where sine was on top and then cosine was on bottom. And then I have to do the bounds. So I know it started at 0 and it ended at pi, but where did it break apart? I'll have to set those two equal to each other. So hopefully we remember our trig. Where does sine equal cosine? Sine and cosine are the same at pi over 4. So that would be my bounds there. It would be to pi over 4. All right, and then I have, so I should write that in. I'm sorry. Let's write that in. I thought I had that. There it goes, pi over 4, and then pi over 4. There we go. Then I'll do the antiderivative. The antiderivative of cosine is sine. The antiderivative of sine is negative cosine, but I already have a negative, so I'll have a negative cosine, and then that's the one I would need to evaluate from 0 to pi over 4, plus the antiderivative of sine is negative cosine of x minus, and then the antiderivative of cosine is just sine evaluated from pi over 4 to pi. A bit tricky, so be patient with yourself. We have to keep track of all of the derivatives and integrals of sines and cosines. That's the stuff from Calc 1. Start plugging in your values. So if I plugged in pi over 4 first, sine of pi over 4 was root 2 over 2. Cosine of pi over 4 is root 2 over 2 minus. And then if I plug in 0 into each of those, sine of 0 is 0, but cosine of 0 is 1. So keep track of that. You don't want to lose those along the way. And then plus, and then I'm going to now plug in pi over here. Cosine of pi is -1. Sine of pi is 0. If I plugged in pi over 4, I would get negative root 2 over 2 minus root 2 over 2. And then you should be able to simplify, combine your like terms. Make sure you know how to simplify and combine your like terms on your own and leave it as an exact simplified value of 2 root 2. And it's units squared because we found an area. Ta-da! Okay, let's do another one. I think it's worth our time to keep on practicing. Find the area of the region bounded by, I'll graph these really quick, y equals x squared, which looks a little something like that. And y equals 2 minus x. You can use your graphing calculator if you need, but hopefully you know that has a y-intercept of 2 and a slope of -1. There's my y equals 2 minus x. And there was another one, it looks like x equals 0. Don't forget to graph that one. X equals 0 is the y-axis. Maybe I'll draw that in a different color. X equals 0 is the y-axis. I had to be a little dramatic about there so you can see. And then this now is my shaded region. What I'm looking for is bounded by all 3 of those. So bounded by all 3 of those would be this small little sliver or small little segment, I guess, up there on the left. I should have been a little bit more clear, and I apologize. I think this one has a typo, so let me fix that really quick. I actually meant to say, of course, in quadrant 1, because if it were in quadrant 2, it would have been that shaded region over there. So I apologize. I definitely meant to say in quadrant 1 there. Okay, so now we have that. We have our little shaded region. You can draw your sliver to help you visualize. Technically, remember there are infinitely many slivers. So one more time, we can see that the area would be, it looks like the 2 minus x is on top. The x squared is on bottom. Your bounds, you would have to figure out where the 2 intersect each other. So to set those equal to each other, I ended up with an x squared plus x minus 2 equals 0, which can factor as an x plus 2, x minus 1. So I end up with x equals -2 and x equals 1. So here's my 1, -2. It looks like it's over in the second quadrant. And because this question asked for the first quadrant, we don't care about that one. So my bounds, it looks like, are from 0 to 1. And then you integrate 2x minus x squared over 2 minus x cubed over 3 evaluated from 0 to 1. Plug in 1, then plug in 0. Simplify your work. Ta-da. All right, let's keep going. We're on a roll. Find the area of the region bounded by x equals y squared and x equals 9. Just as a reminder that sometimes the equations are given to you a little bit different. So you need to remember that x equals y squared is a sideways parabola. Make sure you have things labeled. And then x equals a number is a vertical line. So here's my x equals 9. This is my shaded region. There's more than one way I could do this problem, but this is a great example of one where there's because there's more than one way you get to choose. If I choose my regular, quote unquote, regular dx sliver, that would be fine, except for the parabola is on top and on bottom. And so I would have the y equals the square root of x to be on top, and then y equals the negative square root of x to be on bottom. No problem, that would work. That really, truly would work, no problem. Or I could have chosen my dy sliver. And remember all of those slivers, it looks like they all have the x equals 9 on the right side and the x equals y squared on the left. That would also work. So I'll stick with the dy sliver just so we can have the extra practice. So x equals 9 was on the right side and x equals y squared was on the left. And so it's always going to be the right minus left when you're doing a dy sliver. You might think of it as just bigger minus smaller. That's a little bit more helpful sometimes. And then I need to find those bounds. So if I were to set those two equal to each other, hopefully you can see that they intersect on the y-axis at -3 and 3. And then of course you can go through and do that antiderivative. That's a fairly straightforward antiderivative. Maybe pause to make sure you know how to do that antiderivative. And I got the answer of 36. Ta-da. All right, let's do another one. All right, so now I have find the area of the region bounded by x equals, there we go, x equals y cubed and x equals 3y minus 2. So I've drawn the picture here. You can use your graphing calculator, or hopefully you know how to graph those. And it looks like this is the shaded region here. I'm going to come up with the same idea as what I've done before. There's more than one sliver choice. If I do my regular dx sliver, that would be just fine. If I did the dx sliver, I would have to rewrite those to be a y equals, which is totally fine. Let's go through and do that. Let's practice with that. If I were to do that dx sliver, then I would have to have my area is going to be the integral of top minus bottom, which if I were to get y by itself, let me keep the colors correct. If I were to get y by itself, it would be y is equal to x plus 2 all over 3. And this one would be a y equals the cubed root of x. And so then that integral would become the top, which was x plus 2 all over 3 minus the bottom dx. And I need to find their intersection points. It's always going to be worthwhile to find those intersection points. They happen to intersect at 1. I'm not really sure why there's 4 labeled there, sorry. And they intersected also at -8. Hopefully you guys can see that okay. If not, feel free to use your graphing calculator to figure out where those two intersect. So in that particular case, then that would have gone from -8 to 1, and you can go through and do that integration, no problem. Or if you wanted to, it's also worth our time to notice that I could have done the other sliver. And if I were to do the other sliver in that same shaded region, if I were to do my dy sliver, then I don't have to get y by itself. I can leave them as they're already given to me as an x by itself. And then that would be the integral of the right minus left, which would be y cubed minus 3y minus 2. Don't forget to distribute that negative, so you need that parentheses. And then you would need the y bounds, and those y bounds were from, it looked like this was the y value of -2 to the y value of +1. And then I could do the antiderivative from there. So let me do the antiderivative right away, which would become y to the 4th over 4 minus 3y squared over 2 plus 2y. I distributed the negative and did the antiderivative all at once. Plug in your values for 1, plug in your values for -2. Let's go through and do that even. If I plugged in 1, I would get 1/4 minus 3/2 plus 2 minus. If I plugged in -2, I would end up with a positive 16/4 minus, let's see, 2 squared is 4 times 3 is 12 divided by 2, minus 4. And then you can type that into your calculator and see what you end up with. Ta-da! All right, that'll be the same idea. That's the general idea for 2.1. We'll do some similar videos for each of the sections throughout the semester. There's plenty of these that you're going to want to practice on your homework, as well as stuff that you're going to want to be writing out to practice for your quizzes. You can use your notes on your quizzes, but you won't be able to use your notes on your exams. So use the quizzes as a chance for you to practice if you can do this stuff without looking at your notes. Look at your notes if you need for the quiz, but practice at least a couple of times without looking at your notes. All right, thanks guys.